Okay, to get you started with your in-class exercise, I want to go over a little bit about the max interval problem that we've seen before. So with the max interval problem, before we saw that there was an n cubed algorithm and an n squared algorithm, and you should have done some times for each of these. And when you timed them, you'd see for larger and larger input sizes, then the time got greater and greater. And that's because an order n squared algorithm gets really big really fast. So it doesn't take a very large input size to have an incredibly large output time, time to completion. And if we consider then the order n cubed, well, that's even worse. And so before, we saw that you could have numbers, input sizes for the order n cubed algorithm up to about 10,000 would be as large as you could reasonably run it for a reasonable amount of time. So remember, for the order n cubed algorithm, if we had a sequence like this, what did we do? Well, we started here, and then we summed up this value, this interval, then this interval, then this interval, then this interval, then this interval, and finally this interval. And we did the sum each time. So we did 5 minus 1 for this, then we did 5 minus 1 plus 6 for this one, and then we did 5 minus 1 plus 6 plus 9 here, and we kept a running sum each time. Now this is for the order n cubed algorithm, where we actually do the sum each time. We do the sum each time. And here likewise we'd add them all up. So with this then, the next thing that we would do, and it's going to be kind of hard to draw, but we'd have all of our intervals starting at 1. So then we do starting at minus 1, starting at minus 1, starting at minus 1, starting at minus 1. And then we'd have minus 1 plus 6, minus 1 plus 6, and then minus 1 plus 6 plus 9, and so forth. All right, this would continue going on, and we have to do a running sum each time. So we're adding these up. Each time we add a new interval, we have to start from scratch and say 5 minus 1 plus 6 plus 9. Then for this one, minus 3. So we're redoing the partial sum each time, but that's the naive n cubed algorithm, and that's one of the reasons that makes it so slow. Okay, how do we optimize this? One of the things that we should realize is that a maximum interval will never start with a negative number, and it will never end with a negative number. So we know that no interval that is the maximum is going to start with a negative 1. Why? Well, we'd throw that out and we'd start with 6, and we'd get a bigger max interval. So we would never start with a negative number. Likewise, we would never end a maximum interval with a negative number. So what we can do is, as we move up, if our starting number is a negative, forget that whole thing and just go to the next number. We can eliminate this entire inner for loop by just saying, wait a minute, it starts with a negative 1, forget it. Likewise, when we have, I didn't draw it up here, when we did this, we move forward and we see we get a negative 3. So it starts with a positive number, but if we ever hit a negative 3, we're like, oh, I'm not going to add up each of these numbers. It ends with a negative 3. So likewise, we can cancel out anything that ends with a negative 3 and not have to do this inner sum. Remember, with an n cubed, you're going to have a triply nested for loop, and the innermost loop is what sums these up. So we would skip this would be skipping the innermost for loop, the tightest loop, and then this would be skipping over the entire second for loop, the middle for loop would skip over this. With this, then you can see that we're going to eliminate a lot of these partial sums by doing this. So this will still be an n-cubed algorithm. It will still have terrible performance, but we can make it better by looking at that particular speed up. And so when you look at this, your task is going to be to take your working code for max interval that you had for a previous in-class exercise and use this technique of skipping over starts and stops of the intervals that have negative numbers at the tail ends, either at the beginning or at the end or both. We're going to skip over those. Now this is going to optimize the algorithm. We're going to see better performance, but it's still going to have that characteristic n cubed. However, you can do it for larger and larger numbers. So you'll want to have working code to start this off, working code for the previous max interval, and you'll be running it for the, once you do that, you'll be running it for the original algorithm. So run it for each of these, time how long it takes, and then have a separate program for your optimized and see how long it takes, and calculate the ratio here. Now realize that these are still only going to run up to about 5,000 before it takes a long time, well, for about a minute or two, but it starts to take a long time. And we've got this. Here, this is for the n squared algorithm. You're going to do the same thing. So make sure you're starting with an original algorithm that is correct and also doesn't have any optimization in it. Then for this in-class exercise, you'll optimize it, and then you'll be running it for the new time, and so you should see a speed up ratio here. Now the one caveat is that when you use the order n squared algorithm, for the order n squared algorithm, if you want, when you move forward, you can kick out the big chunks, but remember that there's no inner for loop. I'm sorry, there are only two for loops. You don't have a third inner for loop. And that's because you're always doing the running sums. So in this case, for the n squared, you can't kick this one out. You can't kick this one out because you're going to need the running sum for your next iteration. So you won't be able to save anything running through the by looking at the end numbers, because you're going to need that. But realize that for the n squared, you're not adding each one up. All you're doing is you're having a running sum, and you're adding in the rightmost new element and creating a new running sum there. So the n squared cannot be optimized as much using this technique, but the n squared algorithm was way better to begin with anyway. However, the n squared algorithm still can eliminate blocks like this, which would be the second for loop, the inner for loop, second inner for loop. Okay, so make sure that you start with a original correct running algorithm, and then your assignment is going to be to develop that optimization and run it for these same values to see how much you can speed it up.